In the summer of 2025, a telescope in the mountains of Chile caught a faint point of light moving in a way nothing born inside our solar system ever moves. Weeks later, NASA's James Webb Space Telescope turned toward that same object and detected a molecule that had never once been directly confirmed on anything from beyond our solar system in the entire history of astronomy. And months after that, a completely separate measurement suggested this object might be twice as old as the Sun itself, a wanderer that had been drifting through the galaxy for roughly 10 billion years before it ever crossed paths with us. This is the story of 3IATLAS, the third confirmed interstellar object ever detected passing through our solar system. What James Webb actually found when it studied it. And why? Despite what you may have heard online, every piece of real data gathered on this object points to something far stranger and far more scientifically valuable than the alien spacecraft rumors that have followed it around since the day it was found. Stick with me, because the actual confirmed findings here are wild enough without any exaggeration. And if you want more real discoveries explained the way scientists actually understand them, subscribe now, because there's more coming out of this story. Let's start with why an object like this is such a big deal in the first place. Because for most of the history of astronomy, this category of objects simply didn't exist as far as we knew. Every comet and asteroid we'd ever tracked going back centuries was born inside our own solar system, orbiting the sun the way everything else out here does. Then in 2017, astronomers detected something called 1I Oumuamua, a strange, elongated object moving on a trajectory that made clear it hadn't formed here at all. It had come from somewhere else entirely, another star system, flung out into the galaxy and eventually passing close enough to our sun for us to notice it, before continuing on its way out of the solar system forever. 2 years later, in 2019, a second interstellar visitor turned up, a genuine comet named 2I Borisov, confirming that Oumuamuas hadn't been some once-in-a-lifetime fluke. Objects from other star systems really do pass through our own from time to time. We simply hadn't had the tools to notice them until recently. Then, on July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System, a network of survey telescopes designed primarily to watch for objects that might threaten Earth, picked up a faint point of light at a facility in Rio Hurtado, Chile. Initial calculations on its trajectory confirmed what astronomers had been watching for ever since Oumuamua. This object, too, was interstellar, moving far too fast, and on a path far too steep to have ever been born anywhere in our own solar system. It became the third confirmed interstellar object in human history, and it was given the designation 3IATLAS, named for the survey that found it. It's worth understanding a little about the system that actually found this thing in the first place, because ATLAS wasn't built with interstellar objects in mind at all. The Asteroid Terrestrial Impact Last Alert System is a network of automated survey telescopes, with stations spread across multiple continents, designed primarily as an early warning system for asteroids that might be on a collision course with Earth. It scans large patches of sky repeatedly, comparing images night after night to catch anything moving against the fixed background of stars. The same basic principle astronomers have used since Pluto was first discovered nearly a century ago. Just automate it and running continuously, instead of relying on a person manually flipping between photographic plates. ATLAS wasn't specifically hunting for something from another star system on July 1st, 2025. It simply happened to be the system that noticed the movement first, and once follow-up observations confirmed just how unusual that movement actually was, the rest of the world's major observatories quickly followed. Within weeks, Hubble had captured its own images of the object, and NASA's Sphere-X observatory, along with Webb, joined the effort as well, each instrument contributing a different piece of the puzzle, sharpening estimates of the comet's size, its surface properties, and eventually its detailed chemistry. Early observations from ground-based telescopes painted a preliminary picture. The object showed a distinctly reddish color in reflected light, similar to certain classes of asteroids, and consistent with the coloring already seen on both Oumuamua and Borisov before it. Researchers tracking its brightness over time calculated a rotation period of somewhere around 16 to 17 hours, and its light curve showed relatively little variation, suggesting a nucleus that wasn't wildly irregular in shape. All of that was useful, but it was fundamentally surface-level information, color and rotation, not the actual chemistry of what this thing was made of. To get that, astronomers needed an instrument capable of reading its light apart into individual wavelengths, and that meant turning to the James Webb Space Telescope. Webb's first look at 3IATLAS came on August 6, 2025, using its near-infrared spectrograph instrument while the object was still approaching the Sun. What it found immediately marked this comet as chemically unusual compared to virtually everything we'd ever studied that actually formed in our own solar system. Typical comets from our own solar system, when they warm up near the Sun and begin releasing gas, tend to be dominated by water vapor, since water ice is by far the most abundant frozen material in most comets we've studied up close. Webb's pre-perihelion measurements of 3IATLAS found something almost inverted. Carbon dioxide accounted for roughly 87% of the total gas being released from the comet, while water made up only about 4%, an extraordinarily lopsided ratio that immediately told researchers this object had not formed under conditions anything like the ones that shaped the comets native to our own solar system. If a discovery built on real, peer-reviewed data instead of speculation is the kind of thing you want more of, drop a like on this video right now. It genuinely helps this content reach more people who'd get value out of it. And the first Webb observation happened before the comet had even made its closest pass by the Sun, meaning researchers still had a second, arguably even more valuable opportunity ahead of them. 3IATLAS swept through its perihelion, its closest approach to the Sun, in the fall of 2025, and as it began moving back outward afterward, freshly warmed and actively venting a bright coma of gas, astronomers turned Webb toward it again. This time, they used a different instrument entirely, the Mid-Infrared Instrument, or MIRI, capturing spectroscopic data on two separate dates, December 15th and 16th, and again on December 27th, when the comet sat at heliocentric distances of roughly 54 astronomical units from the Sun. Those observations captured absorption features from water, carbon dioxide, and remarkably, a clear signature of methane gas, along with a faint trace of nickel. It's worth understanding why researchers used two completely different Webb instruments across these observations rather than sticking with just one, because each one is built to read a different slice of the infrared spectrum. The near-infrared spectrograph used in the August 2025 observation is tuned to detect gases like water and carbon dioxide at shorter infrared wavelengths, making it well suited for an initial chemical survey, while the comet was still relatively far from the Sun and not yet producing an enormous amount of gas. The mid-infrared instrument used for the December observations reads a longer stretch of the infrared spectrum entirely, the range where fainter, harder to detect molecules like methane and trace metals like nickel tend to show up most clearly, but it generally requires a brighter target to work with. Waiting until after the comet's closest pass by the Sun, when its ice was actively boiling off into a much brighter surrounding coma of gas, gave the MIRI instrument exactly the kind of signal it needed to pick out those fainter details that the August observation alone couldn't have captured. That methane detection is worth pausing on because it represents something that had never been directly confirmed before on any interstellar object. Every previous hint of methane on objects like this had been indirect or inconclusive. This was the first time astronomers had ever directly detected methane gas escaping from something that originated outside our solar system. According to the researchers analyzing the data, that methane had almost certainly been locked away inside the comet's nucleus as ice since long before it ever encountered our Sun, only converting into gas as the comet's surface warmed during its close approach. What made the detection particularly interesting to the team studying it was the timing. The methane signal didn't show up right away as the comet first began heating up. It appeared later, after a delay, a detail that researchers say hints at how deeply that methane ice may have been buried beneath the comet's surface, requiring more sustained heating before it could finally reach the surface and sublimate into detectable gas. Webb's December observations also reinforced what the earlier August data had already suggested. The comet remained unusually rich in carbon dioxide relative to water, even after its closest solar approach, a pattern researchers say points toward a formation environment and an overall chemistry very different from the vast majority of comets that formed inside our own solar system. And as 3IATLAS continued moving farther from the Sun following those December observations, Webb picked up on something else, a sharp decline in overall gas production, with water showing the steepest drop of all. Researchers describe that as exactly the kind of behavior you'd expect as a comet gets less direct heat from the Sun, its surface cooling, and less of its ice being vaporized into visible gas. A reassuring sign that this object, however chemically strange, is still behaving according to well-understood cometary physics. If you found the methane story as fascinating as I did while researching this, drop a comment letting me know. It genuinely helps me figure out what to cover next. It helps to sit with what an age estimate like 10 to 12 billion years actually implies about this object's entire history before we ever knew it existed. The Milky Way galaxy itself is estimated to be roughly 13.6 billion years old, meaning 3IATLAS, if these age estimates hold, likely formed when the galaxy itself was still relatively young, around a star system that has long since scattered, merged with other stellar populations, or simply drifted apart entirely over the intervening billions of years. This object has spent the overwhelming majority of its existence not orbiting any star at all, but drifting alone through the vast, cold space between stars, the same kind of environment scientists have only recently begun directly sampling, using instruments like the Voyager spacecraft on the edge of our own solar system. For 3IATLAS to have survived that journey largely intact, still carrying identifiable ices and chemistry billions of years later, and then to happen to pass close enough to our own sun for us to notice and study it in detail, represents an extraordinarily rare cosmic coincidence, one that gave scientists a genuine physical sample of material from a wildly different era of the galaxy's history, delivered essentially for free, without anyone needing to build a spacecraft capable of reaching it. Here's where the story gets genuinely remarkable, though, because chemistry alone wasn't the end of what Webb was able to tell us about this object. A separate and more detailed analysis, published in the journal Nature on June 22nd of this year, looked specifically at the ratios of different carbon and hydrogen isotopes present in the comet's gas, including deuterium, sometimes called heavy hydrogen, an isotope that carries an extra neutron compared to ordinary hydrogen. Those specific isotope ratios turned out to be unlike anything found in comets that formed inside our own solar system, and researchers say the results genuinely surprised the team studying them. By working backward from those chemical fingerprints, astronomers were able to estimate the environment in which 3IATLAS most likely originally formed, and the numbers that came out of that analysis were startling. Current estimates place the comet's age somewhere between 10 and 12 billion years old. Our own solar system, by comparison, is roughly 4.5 billion years old. If those estimates hold up, 3IATLAS isn't simply older than the Sun. It could be more than twice as old, making it, based on current data, the oldest comet ever directly studied by scientists, a frozen relic that had already existed for billions of years before our own Sun and planets ever began to form. A separate but complementary study using the European Southern Observatory's Very Large Telescope, led by astronomer Cyril Oppetom at the University of Edinburgh, examined a different chemical angle entirely, analyzing the specific carbon and nitrogen isotope varieties present in a compound called cyanide detected in the comet's coma. That independent measurement lined up with and reinforced the broader picture Webb's data had already painted, an object built from genuinely ancient material, chemically distinct from anything native to our own solar neighborhood. Researchers involved in this work have been direct about why these specific measurements matter so much beyond simply being a curiosity. Stephanie Milam, a scientist at NASA's Goddard Space Flight Center and a co-author on the Webb study, put the broader significance plainly, noting that finding these rare isotopes is genuinely fascinating on its own, but that the bigger picture researchers are actually chasing is the possibility of prebiotic chemistry occurring elsewhere in the galaxy, the same basic kind of chemical building blocks that, as far as we currently know, only ever led to life in one single place in the entire universe, right here on Earth. An object like 3IATLAS gives scientists a genuinely rare opportunity, a direct physical sample in the form of gas and dust, of chemistry that formed around an entirely different star, under entirely different conditions, billions of years before our own solar system ever existed, arriving close enough for our instruments to actually study it directly rather than simply theorize about it from a distance. Now, it would be dishonest to tell this story without addressing the elephant in the room directly, because 3IATLAS has attracted an unusual amount of public speculation since the day it was discovered, some of it suggesting the object might not be a natural comet at all, but something artificial, potentially even extraterrestrial technology passing through our solar system. It's worth being completely clear about where the actual evidence stands on that question. Every single measurement gathered by Webb, by Hubble, by ground-based observatories, and by NASA's own tracking instruments describes behavior entirely consistent with a natural comet. It has a rotation period. It has a coma made of sublimating ice. Its gas production rises and falls in direct response to its changing distance from the Sun, exactly the way solar system comets behave. Its chemical composition, while genuinely unusual compared to solar system comets, is still made up of completely ordinary cometary ingredients, water, carbon dioxide, methane, dust, and trace metals, not anything that would suggest engineered materials or technological origin. NASA and the broader astronomical community studying this object have treated it, consistently and without hesitation, as exactly what the data shows it to be, an ancient, naturally formed comet from another star system. The genuinely remarkable part of this story was never that it might be artificial. It's that real, natural cometary material, potentially twice as old as our own Sun, happened to drift close enough for our best instruments to study it directly before it disappears from view forever. And that disappearance is coming, sooner rather than later. Because 3IATLAS came from outside our solar system in the first place, it isn't in any kind of stable orbit around our Sun the way the planets and most comets we track are. It's simply passing through on a trajectory that will carry it back out into interstellar space permanently, never to return. Astronomers have been racing to gather as much data as possible using every instrument available specifically because this window won't stay open. Once the comet moves far enough away and grows too faint for our telescopes to resolve any further detail, whatever data we've managed to collect by that point will be all humanity ever has on this particular object. There's no follow-up mission planned to chase after it. There's no way to send a spacecraft to catch up with something moving this fast on a one-way trajectory out of the solar system. Webb's December 2025 observations and the isotope analysis published this past June may end up being close to the final word on 3IATLAS that science ever gets to write. It's also worth remembering how differently this particular visit has gone compared to the two interstellar objects that came before it. Oumuamua was discovered only after it had already made its closest approach to the Sun and was already speeding away, giving astronomers just a matter of weeks to study it before it grew too faint to observe in any detail, and it turned out to be too small and too dim for instruments at the time to ever capture a detailed chemical spectrum of its composition at all. Borisov, discovered 2 years later, gave researchers a somewhat longer window and was confirmed as a genuine comet, but the instruments available at the time still couldn't extract anything close to the level of chemical detail Webb has now pulled from 3IATLAS. This third visitor arrived at a moment when Webb was already fully operational and available to turn toward it almost immediately, which is a large part of why this particular object has produced by far the richest scientific data set of any interstellar object discovered to date. Timing, as much as the object itself, is a genuine part of why this story turned out to be as detailed as it has. So, what does all of this actually add up to? In the span of less than a year, astronomers went from spotting a faint moving point of light in a Chilean sky survey to confirming it was an interstellar visitor, to directly detecting methane gas from beyond our solar system for the first time in history, to estimating that the object itself may be twice as old as the Sun, built from chemistry unlike anything found in our own cosmic neighborhood. It's only the third object of its kind ever confirmed, following Oumuamua in 2017 and Borisov in 2019, and every single one of those discoveries has come in less than a decade, a pace that strongly suggests these objects have been passing through our solar system all along, and we simply lacked the tools to notice them until very recently. That pace is only expected to accelerate from here. A newly operational survey telescope, the Vera Rubin Observatory in Chile, began its full scientific operations recently with a specific design goal of scanning the entire visible sky repeatedly and rapidly. Exactly the kind of systematic coverage that's most likely to catch the next interstellar wanderer far earlier in its approach than Atlas managed to catch this one. Astronomers involved in that project have already suggested that finding several more interstellar objects over the coming years, rather than waiting most of a decade between each one, is a realistic expectation. If that holds true, 3IATLAS almost certainly won't be the last messenger from another star system to drift through our neighborhood, carrying chemistry billions of years older than anything the Sun has ever produced. And each new one will arrive with a telescope like Webb already standing ready to read exactly what it's made of. If stories like this, grounded entirely in real published research instead of exaggerated headlines, are what you come here for, subscribe to this channel and turn on notifications. Because 3IATLAS is still out there, still being observed, and there's a real chance the next round of data adds something even stranger to this story before it disappears for good. Thanks for watching, and I'll see you in the next one.